Good afternoon. Today in my lecture series, now we are going to discuss about the second order system. The most of the practical systems they belong to the second order system. So now in today's lecture series we will discuss what are the different types of second order system is available and how their responses are going to be. So just consider a closed loop transfer function, the block diagram of a closed loop transfer function given by or represented using this. So this it is a closed loop transfer function where the input is R of s and the output is C of s, and the transfer function is given by omega n squared divided by s squared plus 2 zeta omega n. So this is zeta omega n. So consider the block diagram of the second order transfer function. So now the closed loop transfer function it is given by C of s by R of s is equal to, it is a unity feedback system. So when we find the closed loop transfer function, it is given by omega n squared divided by s squared plus 2 zeta omega ns plus omega n squared. So now this is the standard representation of a second order control system. Now the denominator, when it is equated to 0, now this equation you call it as the characteristic equation. This equation is called as the characteristic equation, which represent the poles of the system. So now the roots of this characteristic equation, now they decide the system stability and other things. So the roots of the denominator equation, it is given by, it is a quadratic equation. Now when you find the roots, it is given by s1 comma s2 is equal to, there are two roots, so s1 and s2, which is given by z minus zeta omega n plus or minus root of zeta squared minus 1 whole thing divided by, it is 2, whole thing divided by 2. So it is according to the equation minus b plus or minus root of zeta squared or root of b squared minus 4ac divided by 2a. So now the 2 everything it gets cancelled, so I'll just take off this. So the remaining equation of this equation is the roots of the characteristic equation. So now in this case, now when there is the first case, now when zeta is equal to 0, when you substitute zeta is equal to 0, now the equation, like it is nothing but the roots s1 and s2. So zeta is equal to 0, so you get minus 1, so that is minus j. So this equation, now here you can see it is just having only the imaginary part. So when zeta is equal to 0, such a system you call it as the undamped system. It's called as the undamped system. So where the zeta, it is nothing but, it is called as the damping ratio. The zeta over here, we call it as the damping ratio, now which decides the type of the system, the second order system. So in such case, when zeta, the damping ratio is equal to 0, the system we call it as the undamped system. There are no damping components. That is, you can see it is just only the oscillations. Similarly, the second case, now when zeta is equal to 1, when zeta is equal to 1, now you can see now this term it becomes 0. So we are left out with zeta is 1. So it is s1 comma s2 is equal to minus omega n. So here in this case the roots are equal. Okay, you don't have any imaginary part. Now such a system you call it as the critically damped system. Such system you call it as the critically damped system. That is, when zeta is equal to 1, you call it as a critically damped system. Now the third case, now when zeta is greater than 1, the third case when zeta is greater than 1, so obviously now you will have a term over here. So your s1 comma s2 it becomes minus zeta omega n plus or minus root of zeta squared minus 1. Now here you can see it is the roots are real and unequal. Such a system you call it as the overdamped system. Such a system you call it as the overdamped system. And the last case, that is when zeta is lesser than 1. So when zeta is lesser than 1, now this equation becomes, that is S1 comma S2 is equal to minus zeta omega n plus or minus. Now I can write this equation as minus 1, I'll take it common. So this equation becomes 1 minus zeta squared. So which I can write it as minus zeta omega n plus or minus. I'll take this minus 1 outside, so it is j. So then it is omega t. That is, it is omega n into, so just a small change. So here I'll get minus b squared minus 4ac divided by 2a. So in this case, our equation becomes, so here it is minus j outside. So omega n into root of, so here I'll get omega n into root of 1 minus zeta squared. Okay, so as I told you, here you get a small change. So here it is omega n into root of zeta squared minus 1. So here also it is omega n. So in this case it is omega n into root of this whole thing. So omega, now where omega d, you call it as the damped frequency of oscillation, which is given by omega n into root of 1 minus zeta squared. So now here you can see the roots. In this case, that is when zeta is lesser than 1, they are complex conjugate. The roots are complex conjugate. So most of our practical system lies in this range. So you call this as the underdamped system. You call it as the underdamped system. So most of our practical control system are underdamped system, and the most suited value for zeta is 0.7. Most of our control system lies with this value for best results. And the critically damped system, that is zeta is equal to 1, most of the so most of our system, as I told you, it is zeta is equal to 0.7, 0.7, that is the underdamped system. And this critically damped system, our robotic system comes under the critically damped system, where your zeta is equal to 1 in this case. And here it is zeta, now it is omega n over here, so it is omega n, just kindly make this change, so it is minus j omega n. So therefore, our second order control system, they are classified based on the damping ratio. So when zeta is equal to 0, now you call that system as the undamped system, which doesn't have any dampness, and this system is of not used in any practical case. We will just look into that in the next series. And when zeta is equal to 1, you call it as the critically damped system, and most of the robotic system falls under this category. And when zeta is greater than 1, you call this system as the overdamped system. And finally, when zeta is lesser than 1, you call that as the underdamped system, and our more practical control systems, they fall under this category. So in today's lecture series, now we have discussed about the different types of second order system based on the damping ratio. Thank you.